Right, let's see if this works.
Alright, so what we have here is, this is the problem statement as you have seen before. We're trying to find out a solution for this. The first thing you should understand is, this is a second order nonlinear differential equation. And as it turns out, there is no solution in the usual form. If you're given a differential equation, you'll actually use something like separation of variables to find a solution. Okay? There is no solution of that kind. So what we do is we try to figure out an algebraic solution to a calculus problem. This is a calculus problem, right? And the solution you're going to see is going to be an algebraic solution. So what we did is we just moved this the right hand side, right? And then we take the cross product on both sides. Cross it with h. What is h? Specific angular momentum. Okay. So that is what we do here, right? Now this left hand side can be written as d over dt of d over dt of r dot cross with h. Okay. So here you can actually check this out. So what is this? It is actually r dot cross with h dot, correct? Minus or plus r double dot cross with h. Okay. So you can say if you include this, it will be r dot cross with h, right?
Are you're taking the derivative of the left hand side?
Right.
So what
And what I'm showing is this can be written as this.
Oh.
Okay. So this left hand side can be written as d over dt of this. And as you see, if you take the derivative of this is the derivative. Okay. This cross with this, or this cross with derivative of this, and then plus derivative of this cross with this. That's what we have done here. Okay. So we are really looking for this, right? The middle term. And you see the middle term here. Right? That is the reason we have this minus. So this minus and this minus cancels out. What remains is in the. But what is h dot? Derivative of specific angular momentum. Why is derivative of specific angular momentum 0? It is. It's a constant, it's conserved, right? We have proved that specific angular momentum or angular momentum is conserved. Always remember, angular momentum is conserved, linear momentum is conserved, and total mechanical energy is conserved. And we have proved all these three, right? So, based on the conservation of angular momentum, this term just goes to 0. Okay? And you can say that this is just this term. Okay? Got it?
Yes. Is the right before the h dot you have those three edges and nothing? Right before in those parentheses?
Right before each zero.
In the parentheses where h is equal to 0, specific, yeah, those three little.
Those three are, you have therefore, right? This is, therefore, this is since or because. Okay?
Like, then how do we get that minus part in the derivative?
This one?
Yeah.
No, this, what I'm saying here is, this can be written as this. And that's what I showed you here. If I take the derivative of this, it's just this part. Right? So minus this, what it will do is, it will cancel the extra term.
All in the
So only the middle term is left,
Okay.
right? You see the middle term is this one.
And in the bird part, the last part, like why did you remove d over dt? The left hand side should have a still d over dt, right?
This one? No, here I am saying this term is actually 0.
Right.
But therefore, this implies that R double dot crossed with H is simply d over dt of R crossed with H. Got it?
Oh.
Right? So this implies that, see, this arrow means implies. Okay? So this is just equal to this. So left hand side can be written as d over dt of R dot crossed with H. Okay? Now let's look at the left hand side. Left hand side, we are trying to figure out this term, right? Now, I have just taken out mu because mu is always a constant. For a given two-body problem, mu is always a constant. Okay? So what do we have here? We have 1 over r cube. R crossed with H is, what is H? How do you define H? That's what it is. How do you define it? Definition is this. You remember R cross V, right? How do you define momentum? How do you express momentum? mv, right? How do you express angular momentum? R cross mv. How do you express angular momentum? Sorry, how do you express specific angular momentum? You just divide that by mass. R cross v. Okay, so this is R cross v, right? R cross R dot. I've just replaced this H with R cross R. Where does this come from?
Wait,
Oh, that's the ABC
Back minus cap rule. This is the back minus cap rule. Okay. So just remember this. Back minus cap. I've shown you this. Check your notes from first lecture. The triple product. This is a triple product, right? Triple product can be expressed as back minus cap rule. Go check what is this back cap, and in your assignment you're required to use this to prove something. Okay? So what you have is we have just applied the back minus cap rule. Alright? And this is how it turns out to be. See, this is A, B, C. And this is BAC minus CAB. Now here what we have is, remember what we said? The vector dotted with its derivative can be expressed as the scalar into its derivative, right? And you also have an assignment here. The first problem in your assignment is this, actually, proving this is equal to this. And if you carefully look in the textbook, this is already proved. You can check it out. Okay? What is R dot R? R dot R is simply R square. Right? That is what you get. Now, so you can cancel 1R square, right? 1R square. You can cancel that, right? So what you're going to get is vector R into scalar R dot minus vector R dot into scalar R.
Wait, is that R cubed equal to R? Cube goes to R.
Huh?
Isn't R cubed is R? Get one for R.
No, see this. What happens here is you can write this as divided by R cube, right? Divided by R cube. So this R goes to square. This R goes to square. Here 1R remains. 1R is still there.
Oh.
Because we want just R square. We want something common.
Alright.
1R remains there. Okay? So you have R, of course square goes, but then it will not be common. Yes.
So the right hand side, I see the 1 over R cubed, but where did the what's the parentheses come from based on what we have over there?
No, this is not. It's not based on this.
So when you say the right hand side, you don't mean the right hand side to that solution?
So this is what we're talking about.
Right.
So LHS and RHS is from here.
Right.
So
I'm saying-
LHS, this is completely left hand side.
Right.
So we are trying to solve for RHS. We are trying to write an expression for right hand side. You see this? You see what it is?
Yeah. Okay.
It's not actually this, it's actually this. Yeah. It's this thing.
Okay.
Okay? This is where we are talking about LHS and RHS.
Okay.
Okay? So this is LHS, this is what we did, and this is RHS. Now, this is clear, right? Now, if you see, the right hand side is expressed as a derivative. I want to try and express the left hand side, the left hand side is expressed as a derivative. I want to try and express the right hand side also as a derivative. Okay? This can actually be expressed as d over dt of minus d over dt of this. So that is what I am trying to show you here. Just take the derivative of this. What is the derivative of this? See, this is something you have to do very efficiently actually. Okay? What is the quotient rule? How do you take the quotient rule? d over dt of vector r over scalar r is what? R into r dot minus r into r dot divided by r square. Right? Correct? So this can be expressed as this. This is exactly the same. Right? It's this terms are shifted, but we can see that, right? Or it is minus of negative of this. I just take this one here and this one there, so it's just negative. Okay? So what I'm saying is this is negative of this. This is equal to negative of this. So this is for the right hand side. Now what we do is we equate left hand side and right hand side. So left hand side is equal to, where did the negative go? This is already negative when we started. Okay? So negative, negative, that becomes positive. So you have mu r over r. And then if you just take this to the, again back to the left hand side, this is d over dt of all that equal to 0, vector 0. Now since this derivative of something is equal to 0, what we do is again we use that something in the parentheses or square brackets is a constant. Okay, this is step 1 or part 1. Okay, you may be asked to derive this, so you have to remember the critical steps. The first step is to dot it with, to cross the equation with h. Alright? So part 2, let's see part 2.
The first thing, like, why do we cross it?
We are trying to figure out, so this is how it works. When we're trying to figure out a solution, we try out different things. Say cross it, dot it, and see if we can arrive at a solution. And if that solution makes sense. This is what makes sense.
This is like a problem that we might get on the test, or it's just like a derivation. It's like a derivation, it's like a problem.
It's a derivation, it's showing you something. It's proving you something very important. Very, very important.
Dr. Sunny,
Hmm.
can you show the breakdown of R double dot cross H? Like how it goes from B, C, R.
This one?
Yeah. No, the one right below. Right above. Yeah. How does it go from that to that?
So you see this, what is the derivative of this? This is the derivative. Okay? Right? It is simply, think about it as A and B. You just apply the product rule, but in the sense of cross products. Product rule is R A dot cross with B dot, okay, plus A dot cross with B. Alright. Now let's do another step and take the dot product of this equation with H. What are you going to get? R dot cross with H. Minus
Did you?
see here, this is a very important concept here. This is actually 0. This is 0. This is 0. Alright. Can you purely in the sense of vectors, can you make sense of this?
It doesn't have anything to do with that. H being 0. It has nothing to do with the vectors.
H is not 0. The derivative of H is 0. H itself is not 0. The derivative is 0. You see? Because H is constant.
And you said, can we make sense of
Can
that?
you make sense of this?
Why is that 0?
Now, you look at this, okay? You can apply scalar triple product. What did we say about scalar triple product? A crossed with A dot with B cross C is equal to B dotted with C cross A is equal to C. We can cyclically rotate, right? Dot product is commutative. Correct? So if I move this here, nothing changes. Right? So we have AH dotted with R cross with B. This is also equal to what?
Is that a G?
Hmm?
C.
Shouldn't that be A? Oh.
See, this is A, B, C. A, B, C. Sorry. This is one vector, this is another vector. I can do dot product is commutative. A dot B is equal to B dot A. I've just changed this to B dot A. Okay? Now look at this as A, B, C. What I want is, I want this B, C, A. Okay? What is B? R dot, right? What is C? H cross with, and what is a vector crossed with itself?
Oh.
Okay. Got it? So this is the reason this is 0. Alright. What is this? Why is this 0? Why is this 0? What is the direction of H with respect to R? H is defined as R cross with R dot. That means H has to be perpendicular to R. Right? A cross B. If A cross B is equal to C, that vector C has to be perpendicular to both A and B. Okay? If this is perpendicular, if H is perpendicular to R, and if you take the dot product, what happens? It's 0 because there is a cosine term involved. Okay. Similarly, why is this 0? Huh?
X cross itself is diagonal between them.
This is 0 because this is 0. We have just proved that C dot H is 0. Okay? And what that means is, this C is called a Laplace vector. And it has significance when it comes to orbital mechanics. C defines a direction of something.
Can you explain what that middle term even sees there again?
Why is this 0? Huh? How is H defined? What did we say about how the definition of H specifically? R cross V or R cross R dot, right? By definition of cross product, the resultant should be perpendicular to both the A cross B. If C is equal to A cross B, C has to be perpendicular to A and B, right? So if H is defined as R cross B, it has to be perpendicular to R and B. So here it is clear that R and H are perpendicular. The angle between them is 90 degrees, right? What is the definition of dot product? It is R dot H is R, magnitude of H into cosine of the angle between them. Right? So the cosine of angle is how much? 90. Right? Cosine of 90 is 0. Sine of 90 is 1 and cosine of 90 is 0. So this becomes 0. Okay? So we define something called Laplace vector, and it says that Laplace vector must lie in the orbital plane. Now, you understand what orbital plane is?
No.
plane, right? It so happens, what are the two vectors which form that plane when it comes to this thing? You have so you have let's say you have the central body here, okay, and you have the orbiting body here, right? What is this? This is the position vector, and the velocity vector would be, let's say, somewhere like this. The orbit has to be this plane. The board has to be the orbital plane. It cannot change. By definition, it cannot change. Okay? And what it also means is H is always in this direction. The specific angular momentum is always in this direction. You see why? H is R cross B.
What you said? A is R cross B.
H is, what is H? Is equal to R cross with B, right? Or R cross with R dot. Okay. Now if I move V here, assuming nothing changes, it's the same V. Okay. Your H has to be in this direction, right? There is no other direction. And this H defines this plane, this orbital plane. It defines this as the plane, and this direction specifically says that the orbit is anti-clockwise. Anti-clockwise. Counterclockwise. Okay? So that H defines the orbital motion. Right? It has to be this. It has to be R cross B. H is not equal to you cannot change the order. Got it? It is always has to be this. R cross with B. It is not B cross with R.
Because then that would be clockwise.
That H is not defined that way.
Yeah, that's what I'm saying. So
Right.
if it was that, it would be,
So if the orbital motion was in this direction, wasn't H is in that direction. Okay, this H always defines the motion. Now, what did we learn here? I gave you a statement in parentheses that H dot is what? H prime, the derivative of H prime is 0. That means for a strictly Keplerian motion, it's always in that plane. That H is not changing in direction, not changing in. If it changes in direction, what happens? The plane itself will change. Change in direction means it will become like this or like this. The plane will change, right? What if the magnitude changes? What happens? The orbit size will change. The plane will remain the same, but the size will change.
so when you mean orbit size, you're saying the direction of H is the orbit? So H is coming out.
So H is, you understand, this relates to direction, right? So this is, if direction does not change, that means this plane is always the orbital plane. Got it? If it was this, if it changed from this to this, it means the orbit plane has moved. Now, by definition, we know H does not change. Right? So this orbit plane is always this plane. What happens if magnitude changes? The direction is the same, but the magnitude changes. The plane is the same. Instead of getting this orbit, you're going to get larger orbit. Both this orbit and this orbit are in the same plane. You realize that most of our planets are in the same plane, except for Pluto. Okay? Most of our planets are in the same plane. Okay? So that is what it means. Now what that also means is this Laplace vector is actually in the orbital plane. Because C dot H can be 0 only if C is perpendicular to H. Right? And for C to be perpendicular to H, it has to be in the orbital plane. Okay. Now let's quickly finish the second part of this derivation. So let's call this A. You have R over R. So I've done nothing except that the C over mu is equal to, is expressed as vector E. Okay? So this is vector E. So what we do is we just divide this whole thing by mu. Right? So you get R dot crossed with H over mu. Okay? Equal to C over mu plus R over vector R over scalar R. Got it?
You say divide the whole thing by what?
Divide the whole thing by mu. Mu. Okay? Here I'm going to write dividing by mu.
Yeah, why do that?
I'll get to why. call this B. All right. So what we did here was
C over mu equals E or dash C over mu is C or E?
E. C over mu cannot be C, right? It's a different constant. Right? We just use E instead of C. So what you're seeing here is we take this equation. This is part A, right? And this was part B. Okay. And this is the complete solution. We divide this equation by mu and move this to the right hand side. You see that? That's happening there.
Can you show that? Yeah.
This is this term. Okay? This is this term moved to the right, and this E is simply C over mu. Alright? You take this and dot this with vector R. R dotted with R plus E dotted with R equal to R dotted with this whole thing.
It's not R dot. It's not R dot.
R vector R. Okay. So R dotted with R. Let's do this. So what we are trying to do is we are trying to figure out a simplified expression for this, and that is what we are deriving here. R dotted with R dot cross with R. What did I do here? This is again simply A dotted with B cross C is equal to.
Did you just take the constant out?
C dotted with A cross B. I've just done a cyclic rotation.
I'm saying that mu, you just took that out, right?
Right. Yeah. The mu is out. Right. that's true. So we are trying to figure out a solution, an expression for this. Make sense?
Yes.
So this is simply this written as this. Okay? The reason we want to do is we want to get that R cross with R dot. Okay? What is R cross with R dot? H. So it is H dotted with H. And H dotted with H is H square.
Say R
R cross with this there is a okay. R cross with R dot. Remember here we had that. That is how H is defined, right? So it is H dotted with H. That is H square. Okay. So if you substitute this here, this is R square over R, which is R, plus R dot E or E dot R is the same thing, equal to H square over mu. How do we write? How can we write this H R dot E? This R dot E can be written as simply R, magnitude of R, magnitude of E into cosine of theta, where theta is the angle between vector R and vector E. Okay? If I substitute this back in B, you're going to get R plus R E cosine theta equal to H square over mu. Okay? And then we take out R, 1 plus E cosine theta equal to H square over mu. Right? That or R is equal to H square over mu divided by 1 plus E cosine theta. Okay? Now just pay a little bit of attention here. What is this R? The magnitude of the position, right? So it tells you where the orbiting body is. H is a constant, right? Mu is a constant. E is a constant. The only variable is this theta. Okay? If you look at R, what R is, this H square, H is constant, right? Mu is constant. E is also constant. Theta is the only variable.
Is that native for the line?
Theta for, so that's what I'll tell you what that theta means. What we do is, so we'll use this figure often. So this is where your central body is, okay? The capital M is. And this, let's denote this by small m or the orbiting body.
In center of mass, right?
Huh?
The capital M is center of mass.
No, this is the central body.
That's M1.
M1 you can say, and this is M2. Got it? This is that R.
This is the distance between
The position vector of the orbiting body with respect to the central body.
and the closer you get M1, the closer it is to 0.
Right. See, this is, if it gets closer to M1, it will just spiral in. Right? So you can say there is atmosphere here. Okay, this is out of atmosphere. This is what we define as vector E. Okay? And this is that angle theta.
So it's just literally how far in the orbit is.
Right. So what it says is, it's orbiting in this direction, okay? Anti-clockwise.
What is the angle that is determining if it's going up or if it's going down?
Right. So this angle will tell you where it is at a given instance of time. So this angle is changing, right? This angle changes, and that is how this r changes. R is strictly a function of this angle. We define this e direction. I'll tell you what that e direction is. So you can say, I told you here that this Laplace vector has to lie in the orbital plane, right? What was h? What is the direction of h? Huh? It's coming out. Your velocity has to be this, okay?
Oh, yes, this is.
So your velocity has to be like this, right? Have you tried to hook something up to a string and then what is the velocity direction? It's kind of tangential, right? Not exactly tangential, but if it is strictly, if there is no centrifugal force, then it is strictly tangential to this curve. But this velocity has to be in that plane, the velocity direction. What happens if that velocity direction is not in the plane? It will come out of that plane.
Well, did you say that h, the magnitude of h is bigger, it makes the orbit bigger? So I'm not.
Right, so h is this direction.
Mhm.
Okay? So this, if h changes, the direction of h changes, this plane itself will change because h has to be perpendicular to the orbital.
But did you say if the magnitude of h is bigger, then the orbit is bigger?
Right, so if h is this, okay, direction does not change, but the magnitude changes. This just becomes something like this. So you can think about this could be a low Earth orbit where the space station is. This could be a geosynchronous orbit where the GPS satellites are. GPS satellites are way far, right? They're way, their altitude is, it has to be a 24-hour satellite. Correct? So this is way outside. Space station, you cannot have space station here. It will be very difficult to access that. Space station is in about what? 300, 400 kilometers. That's it. Right? You cannot go beyond that. Of course, you could, but it's not going to be as accessible. You don't go to GPS satellites and try to repair them. Right? Have you heard about GPS satellites being repaired by a human being? What was the other thing which was repaired by a human being?
Hubble.
The Hubble was repaired by a human being. Scientists went there to repair it. Right? So Hubble had to be in a lower orbit. You understand what a lower orbit is? The altitude is much less. So if you assume that Hubble and GPS satellites are in the same plane, one of the GPS satellites is in the same plane, the angular momentum vector for those two orbiting bodies, the direction is the same, but the magnitude is different. You understand? Okay. So this is what it says. This equation is the solution to two-body problem. Remember what our statement for two-body problem was. It was r double dot plus mu over r cube into r is equal to 0. Typically, if you compare this with any differential equation, let's say d square x by dt plus 2x is equal to some y, right? What are you going to try and do? You're going to try and figure out, as part of your solution, you're going to try and figure out this x. You're interested in getting a solution for this x. What we have here is solution for r. You see it? We have figured out a solution for r. R is expressed in terms of only one variable, that is theta. This is absolutely very important. So what you see here is this is called the solution to two-body problem, the trajectory equation or the orbit equation. And what you have to understand here is h is constant, mu is constant, e is constant. Only variable is this theta. And you can see it here. If I show you here, only theta is changing. for a given orbit. This is for a given orbit. You understand, for a given orbit, right? H will change for different orbits. If you're trying to study one motion of one set of bodies, this H will be constant. Mu will be constant for the mu is a constant for the central body, right? Whether you're dealing with GPS satellites, whether you're dealing with space stations, mu is a constant because they are orbiting Earth. They're orbiting Earth. So mu would be simply the gravitational potential or gravitational attraction force of Earth into the mass of Earth. That is always a constant for a given central body. This H is constant for a given set of body. H is a function of the orbiting body. Okay. And this E is just a defined direction. You see, we've already established that E is constant. This, we know C is constant, right? C over mu, this has to be constant. Because mu is constant, right? So E is constant. If the vector E is constant, obviously the magnitude of that is also constant. Again, this is for given set of two bodies. Okay. E is defined. E is constant for a given orbiting body. Alright? Tomorrow you guys want a session for your assignment is due Tuesday. Have you guys started looking at it?
Can we move the date from Friday? I thought we had discussed it.
You have Monday as well. So Monday will be probably be too late.
Well, for next week, I guess we can do it Friday tomorrow, but for previous session. Next week.
All of you are present today. You guys want a session tomorrow? 2 o'clock? We'll discuss only assignments. Only assignment 1. I'll just give you a hint as to how to start assignment.
We get our notes back. We get our notes back.
That, why don't we take a picture? I need those. I have not graded them yet.
So from henceforth, can we move so we do a different day than Friday? From henceforth, can we do a different day than Friday? Because that's
Sure.